Let me go to these slides. Okay, so we continue on the Bayesian modeling, probabilistic Bayesian modeling. We have seen some application, some examples of application of Bayesian reasoning to some simple distributions, the Bernoulli, Dirichlet, and studied what are their priors and posteriors and what are their estimates. Today we'll continue our discussion still on the application of this Bayesian reasoning for particular examples in the sense that some of the common distributions, both for the likelihood and the priors, and see what are the estimates, what are the forms of the estimates. So today let us start with Gaussian models. I will cover in this order. I will first start with univariate model where the variance is known and fixed. The mean has to be estimated. Mean is the parameter, unknown parameter, and then mean is fixed and variance is the unknown parameter. Finally, both mean and variance are fixed. First, I'll do all these three for the univariate case. Then I will move on to the multivariate case. Okay, so let us quickly go through the known variance or fixed variance. You have some examples in observations x1 to xn, and let's say the temperature of a day. Okay, and this n is.
Sir, we cannot see either any slides.
We cannot see. Okay. Wait. Now can you see?
Yes, sir.
Yes, sir.
Thank you. So we'll start with the Gaussian model. First, we'll start with the univariate Gaussian with fixed variance, univariate Gaussian with fixed mean, unknown variance, both varying mean and variance, and more importantly, we'll go to the multivariate case. So let us go through quickly the single variable case where the sigma or the variance is fixed, and we have n samples x1 to xn drawn from an one-dimensional Gaussian with mean one-dimensional normal distribution with mean mu and variance sigma square. So as you know, this basically means that the likelihood function, that probability that a random sample drawn from belonging to x is xn, random sample xn is some value given the value of mu and sigma square is the normal distribution. I am dropping the constant term. There is a constant multiplier. So this is proportional to this form. All of you is the most common form, e to the power minus xn minus mu whole square divided by 2 sigma square. This is the univariate Gaussian distribution. So this is the this means the single observation xn is drawn from this distribution. This is the probability density function. See, if I assume x1 to xn are independent, then the probability of x, all that means x1 and x2 and x3 up to xn, which I call as capital X, this set, is nothing but the product of this Pn because they are independent. Okay, so it is Px1 given mu square, P into Px2 given mu square up to Pxn. All right. So as we have said, the problem is the following. The problem is like the following. You observe n number of temperatures of a day. I assume that if I know given mu and sigma, temperature is normally distributed, Gaussian distribution. This distribution, it is assumed this distribution. My problem is, and sigma is known and fixed. Let us assume for the moment. And given these n observations, you have to estimate what is the mean of the distribution. Why you are interested in the mean of the distribution? Because if we know mean, sigma you already know, we know everything about the distribution. And then you can generate new xn, generate the temperature of a new day based on this. again, generate means two things. Generate means I know the full probability distribution of the temperature. This temperature is this much likely. This temperature is this much likely. I know the full distribution. That's what I would like to do. And if I know mu and sigma, I can actually do that. So my problem, so this Px given mu sigma square as per our previous definition is the likelihood function, is the likelihood distribution, not function, is the likelihood distribution. So you know in Bayesian statistics along with likelihood, so likelihood is what we come to know from the data, and we have a prior knowledge also, which is the previous knowledge about the something about the distribution. In here, the previous knowledge is we know something about what mu can be. We know that in West Bengal, the average temperature is in say the month of September is 30 degree. So 30 degree has the highest probability. Maybe 28 is little less probability. So this information, this knowledge, somehow we have. So this is encoded by a prior, the distribution of mu value. Which mu, how much likely? We say, this again is our knowledge, and what our knowledge says is that P mu is again a Gaussian. P mu, so mu is distributed according to Gaussian. The mean itself is a Gaussian. Note that this Gaussian and this Gaussian are different. Is the Gaussian likelihood Gaussian? What is the value of temperature given the mean and sigma? And this is the value of the parameter itself. What is the mean? What is the distribution of the mean temperature? Okay. So the prior is known. That means the mu naught and sigma naught of the prior distribution is fixed and known. For the moment, let's assume in fixed and known. If we do a model selection, maybe this will not be fixed also. Okay, so so as you now already know very well that we estimate mu by computing this probability P mu given data, the posterior probability. This is our estimate of mu. This is our estimate, and this is a distribution estimate. That means it gives you full information about mu. What is the value of, what is the probability mu is 30? What is the probability mu is 28? All the probability it gives, as opposed to a point estimate. That means what is the highest, most probable value of mu? Okay, so there are two things. One is what is the distribution of probability distribution of value of mu, and the second is it comes from the distribution itself is what is the most probable value of mu, which we call as the MAP, maximum a posteriori, or a point estimate, as opposed to a distribution estimate. Okay, so we let's say we go with the distribution estimate. That means we have to find out P mu given x, and by Bayes rule, this is this. Px given mu into P mu divided by the marginal likelihood, and Px given mu is the likelihood distribution, which you already know to be Gaussian. So this blue colored Gaussian here, xn minus mu whole square product x1 to xn because of independence, and P mu is a prior, our previous knowledge which we have assumed. It is also a Gaussian with mu minus mu naught, the parameters of the Gaussian. So this mu naught, sigma naught are kind of a hyperparameter of the prior. Initially, we assume that the hyperparameters are given and known. We may also assume that you can vary your hyperparameter. Okay, so this is my posterior distribution. If you just do some algebra, if you just do this multiplication, so it's very simple. So basically, xn minus mu you expand to xn square minus 2 mu xn, and this also you expand. If you do it, then you see that P mu given x also becomes a Gaussian distribution naturally, because you are multiplying exponentials. It will stay to product of two exponential is also an exponential, and the new I'm dropping again the constant factor. This constant factor actually plays the role of a normalizer, in the sense that you know anything which is a probability distribution or a density function, the area under that, any function which is a density function, the area under that curve has to be 1. Okay, so basically if you integrate this function from xn equal to say minus infinity to plus infinity, it gives you some value. And since that has to be equal to 1, you kind of divide it by a constant term or multiply it by a constant term so that the entire thing becomes 1. That's the another property of probability density functions that we require. So that constant is basically a normalizer. Again, I'm dropping that constant because that constant is independent of x. It depends on the integration with respect to x over the entire range. So it's independent of x. And this takes the form e to the power, again a Gaussian. Note that the posterior distribution is again a Gaussian. So what do we call in this situation where the prior and the likelihood and the posterior, the prior and the posterior takes the same algebraic or functional form, then we call it as a conjugate prior. So as if this is a prior, some functional form of the distribution, multiply it by the likelihood and you get a posterior. If the posterior is of the same functional form, this likelihood and prior are said to be conjugates. So this is a conjugate because the posterior is also a Gaussian. But it is a Gaussian with a different mean than the original mean and mu naught and sigma naught. So mu naught sigma naught is the prior. After observing n number of data points, it still stays a Gaussian, but with a revised mu sigma, revised from mu naught sigma naught, a updated form of mu naught sigma naught. What is the updated form? Let's say this is the updated form after observing capital N observation. So I call it sigma n and mu n. As it turns out, if we do again the algebra, I'm not doing it. Again, the algebra is the new sigma n is a harmonic mean of the prior sigma, which is sigma naught, and sigma square of the data. Sigma square is the given mean of the original Gaussian. Original Gaussian fixed mean, we have said sigma square divided by the number of observations. This is the harmonic mean of these two. And mu n is a weighted combination of the original mu naught of the prior and the average value or the mean value of the observations, which we call as x bar. And what are the weighting factors? Weighting factors for mu naught are sigma square by n, sigma naught square by sigma square. Okay, so higher the variance, higher is the weightage for mu naught, and the weightage factor for x bar is n sigma naught square. Note the difference. The denominator is same for both. Denominator is same for mu naught and x bar. The numerator is sigma square for mu naught. Sigma square is the variance of x1 to xn given, and sigma naught square into n for x bar. Okay, so sigma naught square into n for x bar, and sigma naught square, so x bar is kind of the sample mean, whereas sigma naught square is the prior mean. So this cross kind of thing is there, mutual weightage is there. That's my new mu n. Okay, one more thing to note is that if you look at the posterior is a Gaussian, and the mean of the sigma of the Gaussian is not a function of whatever x1 to xn you choose. They don't appear because sigma is fixed. Sigma square is fixed. Only n comes into picture. Nothing else comes into. Xn does not come into picture in the definition of sigma n. Xn does come into picture in your expression for mu n, but it comes in a particular form. It comes as x bar, which is the average of all the xn, x1 to xn. This is the only, note that in the new, you always view it like this. You have a prior knowledge, prior distribution, and you have some observations. All this Bayes rule does is that revises the prior using the observations. It changes the priors. It updates the priors. If it is conjugate, then the functional form of the prior is not updated. It remains the same. Only the parameter values change. Okay, so if we look at the new parameter value, so new parameter value should be a function of the old priors, mu naught, sigma naught, and the data, x1 to xn. The way it is dependent on data is, you see, the only place where data appears is in the form of x bar. What is x bar? As you have said, is the average of x1 to xn, sigma xn by capital N is the average. So this x bar is kind of an average. That means it is a statistics about x1 to xn. It is an aggregated value about x1 to xn. Okay, and in order to compute mu n, we need only these statistics. We don't need individual x1 to xn. We need only these statistics, only this aggregate information. Okay, so such an information will let us generalize it more mathematically. I'm just intuitively saying here is called a sufficient statistics. That's all information about the data I need. I don't need any other information. Okay, it's an aggregate. There is one more thing to be noted is that the sufficient statistics is kind of incremental in the sense that maintainable. That means, see, suppose I look at n points, capital N points, and this is my x bar. If I get one extra point, n plus 1, my x bar just is x bar plus xn by 2, x bar plus xn plus 1 by 2. Okay, it's easily updatable. It's easily updatable, which means is that since mu n is this is sufficient statistics, that means you can update mu n itself by one single addition. You can update mu n as and when you get new data points by one single addition updation, which is very convenient thing to do. You don't need to remember x1 to xn. You need to remember x bar, and when you get xn plus 1, you update x bar. And since mu n is a simple function of this, you can easily update mu n also as you get a new point. So this is computationally a big advantage. Okay, so let us quickly go through the, let me very quickly go through the posterior distribution. Actually, I'll maybe skip it because you can go through the slide. The posterior also, if you remember, how do we calculate the posterior? Posterior is new point x star given old point is new point is by the product rule of probability, x star given mu sigma, and mu given sigma is fixed, so mu given x into d mu integrated over all possible values of mu, integrated over the prior distribution mu. And here again, if you plug in you have already estimated, this is the likelihood, the first term, second term is the second term is the likelihood, the first term is the posterior, first term is the likelihood, second term is the integrated likelihood. So if we I missed it. Mu given x. Second term is the prior. So if you multiply it, you again get the expression for the called the PPD or the posterior predictive distribution, which again turns out to be a normal with mu n, and sigma you see is sort of expanded. The variance is expanded. It is the old variance sigma square plus the variance of the set of data points sigma square. Okay, so you go through it. I'm not going it. Okay. So now let's come to the other case. That means mu is known, sigma is to be estimated. So let's assume as previously that likelihood distribution xn given mu sigma is this. So if you multiply all these likelihoods over n samples, because they are independent, you get this. And sigma square is to be estimated. Let's say we have a prior. I just for example. So the prior is now on sigma square. Prior is now on sigma square. So I don't take a Gaussian prior. I take something called a inverse gamma prior. If you know, so this is the inverse gamma prior. Xn. Where is the inverse gamma prior? Have I written it down? Yes, here is the inverse gamma prior. Inverse gamma prior is p sigma square. So it is a prior on, I directly take sigma square, I don't take sigma. P sigma square is sigma square to the power alpha minus alpha plus 1 e to the power minus beta by sigma square. So this is called the inverse gamma prior. It looks like an Gaussian distribution, but slightly different. You have two hyperparameters, alpha and beta, which controls the shape of the priors. Okay, shape and scale rather of the priors. And so this is my likelihood, this is my prior. If you multiply, again I'm not doing the algebra, you will see the posterior also becomes an inverse gamma. So with some parameters, alpha plus n by 2. So this I'm intentionally skipping quickly because I have to cover more material, but all of you should carefully go through the slides. And if possible, Kevin Murphy or the Barber book where these derivations are done. The posterior is again a inverse gamma, so it is gamma and Gaussian, inverse gamma and Gaussian are conjugates with some parameters. Okay, so next case, again this I'll skip, I'll go, the basic idea is again same as estimating mu, only the priors and these things we are changing. All right, so you take a Gaussian likelihood. I just introduce another definition, which I call, instead of sigma, mu sigma was the parameter, only two parameters of Gaussian. I define lambda to be sigma inverse. Okay, and I call lambda as a precision. It is the inverse. So sigma is kind of the dispersion, how fat the distribution is, whereas sigma inverse measures the inverse of distribution. That means how concentrated or thin the distribution is. Concentration distribution, as if they are more precise. So that's why I call that as a precision, inverse of sigma. So this is my likelihood function, x mu sigma. If I just write it down, this is just a Gaussian, plain old Gaussian distribution. If we write it down, it looks like this. And the prior distribution, see, now there are two parameters, mu and sigma. So prior, note that, should be a joint distribution of mu and sigma. Okay, is a joint distribution of mu and sigma. So I choose my prior as kind of a composite distribution. Okay, so we take the mu part to be a Gaussian and the sigma part to be a gamma, as I have done previously. Okay, so this combination is sometimes called the normal gamma distribution, combination product of normal and gamma distribution. Right. So this is my final prior, how it looks like. And if you work out the posterior, this is from the posterior text. Note here, the posterior is now mu sigma, or rather mu lambda. Lambda is 1 by sigma given x, which is a normal Gaussian again of this form. So Gaussian and normal gamma again of this form. So Gaussian and normal gamma are again conjugates. So this is the final form. Again, algebra you need to work out. I'm not doing it. This is an advanced course. You have to work out the algebra yourself. So mu sigma, mu lambda rather, given x is a normal Gaussian, which is a product of a Gaussian and a gamma. Okay, and the parameters of the Gaussian and the gamma are, these are the expressions. I leave it here. You can interpret sort of. The good thing about all these conjugate priors and all thing is that the final parameters that you estimate, the estimates that you gave, they have very nice intuitive interpretations. Again, I leave this to you as an exercise, because you should be able to do this in future. So you look at this distribution and see, the whole idea is there is a mu naught, which is the prior, and there is a x bar, a sufficient statistics about the data, and these two are combined to get the posterior. Okay, so now let us come to the more important case. Univariate, or rather univariate Gaussians are common. They are still very common, but modern machine learning demands usually multivariate Gaussians. So this is the standard form. You have a normalizing term and e to the power x minus mu. Note here, x is a vector here because you have multivariate. Mu is also a vector, and sigma is a covariance matrix. All right. So you can actually do all this matrix algebra and have all these definitions and do it. There is a very interesting alternate representation of Gaussian distribution multivariate. It's called the information form, where you basically, instead of sigma inverse, you write lambda, capital lambda here, which is sigma inverse. And you have xi, which is kind of sigma inverse into mu. We'll see that these are really important quantities. A xi, which is sigma inverse into mu. It's kind of the variance, mu divided by the variance, the mean normalized by the variance, mu by sigma. So this is an alternate representation. Instead of mu sigma, I write it as psi lambda. Mu sigma, instead of mu, I write just the mean, I write the normalized mean, mu by sigma, which I call psi. And instead of sigma, I write sigma inverse, which is lambda. So if you do these substitutions, you get this form of normal distribution called an information form, which is xt. So here it was x minus mu transpose. That x minus mu business I do away with. It is directly x transpose lambda x, sigma xi transpose lambda inverse xi minus x transpose xi. Okay, and a half on over everything. Okay, so these are sometimes called the natural parameters. Okay, so but the moral of the story is you have two parameters which are enough to characterize a Gaussian, a mu vector and a sigma or the covariance matrix. So what I have done, let us try to visualize. This visualization should be with you. It's already with you probably, but it should be with you throughout. Suppose I have two variables, say y1, y2, and so the covariance matrix sigma will be a 2 by 2 matrix. The diagonal of the matrix are the variance term. That means it is so if you have y1, y2, it is variance of y1, the first term, and the variance of y2, the second diagonal term. So the off diagonal elements are kind of the correlation between how much y1 affect y2. I'm not writing at x1 because x is something else. y1 is affects y2 and y2 affects y1. So these off diagonal terms are kind of the correlation. So what I have done here is that I have plotted what are called equiprobable contours. Because see, it is a bivariate distribution. So in the x and y axis, if I plot the two variables, let's say call them y1, y2, in the z axis, which comes out of the screen actually, is the probability value. So it's a bell-shaped curve. It's a bell-shaped curve. You have to imagine it. I don't know if I can draw it. This kind of, it's a z-axis looks like this. Okay, it's a kind of a bell-shaped curve like this. Okay, and if we cut this, if we take a section kind of like this, you get these contours. You get these contours, right? And it you get a lot of information by just examining these contours. For example, if the correlation is so, if the off diagonal elements are 0, then this should be axis parallel. This should be just rotated and axis parallel. The spread along x-axis is proportional to the first diagonal element. The spread along y-axis is proportional to the second diagonal element. And these cross diagonals, off diagonals are the correlation. So higher the correlation, this ellipse will be, shorter and shorter. So if it was say 0.9 of diagonal elements are say 0.99, these ellipses would rather look like this. Okay, so in the extreme case, it is looking like there is a linear relationship with some disturbance due to noise between x and y. There is a linear thing. So if we kind of draw it, it would look like this. So there is almost a linear relationship. Okay, and as you decrease your off diagonal elements, this property gets destroyed, goes away. So this is for 0.4, and in the extreme case, when there are 0, they are perfectly spherical. There is no correlation between x and y. They are perfectly spherical. Both of them are, and this diameter is proportional is 1. It is, and this diameter is also 1. They are equal. Okay, so they are no longer, this linear relationship is no longer there. Okay, so this is kind of a better picture. So this is perfectly spherical. The size of the sphere depends on these diagonal terms. Depends on these diagonal terms. Right. If the diagonal terms are same, this is a perfect sphere. If the diagonal terms are different, like say here 0.3 and 0.8, there is more spread in the y direction than in the x direction. So it's not a sphere, it's an ellipse. And the moment there are off diagonal terms, they get rotated. This is a negative cross correlation. This is a positive cross correlation. There is also one more thing, property of this covariance matrix, that it should be something like a positive definite matrix. Positive definite matrix means you take any vector, a matrix A is positive definite. If you take a vector x and you get the quantity x A x transpose, it is positive. Why that is so? Because you know that this is finally in the numerator, you will have this x A sigma x term. This has to be positive, otherwise e to the power minus that will not go down, it will go up. So sigma has to be positive definite. Okay, so these are some visualizations, these are some properties of the thing. And this thing, that this off diagonal term or the correlation, the higher it is, more they are dependent, x and y are dependent on each other. This fact we'll use later to devise a new algorithm. Okay, there is some more interesting things to note about Gaussian distributions. So far, we have not made any distinction between the variables, right? So even if we have vector variables, say temperature and humidity of a day, so there are two variables, and I say that they are kind of independent or something. So I treat this entire pair, temperature, humidity, as a single vector x. In many situations, you can actually partition this vector x into two parts or more parts. Say x is divided into one bunch of variables which I call xa and another bunch of variables which I call xb. Now this partition may come from the domain. It may be like it may be say this causes this, or this is dependent on this something. So naturally, if x is partitioned, mu will also be partitioned, and this sigma will also be partitioned, like this sigma A, sigma BP. So now, moment we divide the variables into two groups, you can take marginal over a group. Say I want Pxa and add up over all possible values of the parts xp. So this is my marginalization integration. And I can also find the conditional distribution, that is suppose I know the value of xp. Okay, so earlier my model was kind of I know temperature, I know humidity. I observe temperature, I observe humidity. But suppose I want to study the relation between these two things. Then I go into conditional. So suppose given the value of xb, what is the value of xa? So we are interested in this kind of conditional distributions. Let us explain this with a simple case. Let's say, and then I'll come back to the previous expression. Let's say the xa is just a single variable, y2 or y1, and xb is a single variable, y2. Okay, and so if I look at the joint distribution and look at the contour plots, this look like this. Say it looks like this. Okay, so what I have actually done is that I have kind of I have kind of made the mean, just for visualization, I have made the mean to be 0 at the origin, and sigma I have taken some form. Right. So now what is a conditional distribution? As I have said before, fix the value of, let's say, xa. So in this case, let's say I fix y1 to be 1. And I am interested in this conditional probability. Given y1 equal to 1, what is the probability of y2? And there is this sigma parameter, which is the theta part, the parameter part. Let's say that is fixed for the moment. So given y1, what is y2? Given y1, what is y2? What does this mean? So as I have said before, So this is kind of a three-dimensional bell or a cake, let us say. It is like a three-dimensional bell or a cake, the joint distribution. And this red line is kind of a knife that we are cutting through it, taking a section. And you are looking for the side. What does the conditional look like? You will see that the conditional will look like this. It will also be a Gaussian. It will, the algebra I'm doing, I have done in the previous slide, I'm coming back. It will also look like a Gaussian. Okay, it will also look like a Gaussian. The conditional will also be a Gaussian with mean mu star and variance sigma star. We'll see that mu star will be the original mean of the joint distribution, which is 0, 0 in this case, plus something, So let's say this is the point, this plus something. And this plus thing is nothing but some constant, linear constant time y1. And similarly, there will be a sigma star. There will be a variance. And this sigma star will directly depend on the original sigma. So the thing is that the conditional is a closed form expression, which is a simple combination of the old sigma multiplied by some linear constant into y1. So so here is the expression. So this sigma star is the, here I call it sigma a given b, which takes this form. Note one thing, that the variance actually reduces by this conditionalization process. And this is the new mu. It is the old mu and old the mean of the set of points minus mu multiplied by some variance term. Okay, so you get a closed form expression. So this is another important thing to be noted, like the conditional distributions. If we have two parts of a variable, how does the conditional expressions work out? Okay, one more thing I just mentioned is that I said that it is also a Gaussian with some mu sigma. Here I draw a picture. If my original joint distribution changes from a kind of linear correlation, a perfect correlation, to less correlation and no correlation, then the sigma changes like this. The point to be noted is that if there is high correlation between y1 and y2, this variance is small. Whereas if there is no correlation between y1 and y2, the variance of the conditional is same as before, same as the joint distribution, same as before. There is no variance reduction if there is no correlation. One way of looking at this is that what is this conditional? Is that given y1, what information you have about y2? More the variance, the less precise is your information. So if there is a correlation between y1 and y2, if there is a perfect line correlation between y1 and y2, the variance is less. That means given y1, you have more and more precise information about y2. If y2 is a direct linear function of y1, no probability, direct linear function, then you have more and more precise information about given y1. The less they are correlated, less and less precise information you have. This also we'll use later. Okay, so I just you can do the same exercise that you have done for univariate Gaussian. You can assume some prior. You can assume some likelihood. One common prior is for multivariate is a generalization of the gamma prior that we talked about earlier. It's called the Wishart prior. It's a multivariate generalization of the gamma prior. So just like you have normal gamma distribution, you have a normal Wishart or a normal inverse Wishart distribution. Okay, so these are rather not very difficult to do. If you just write down the expression for this, multiply and do the algebra, many interesting comes out, but you can do it. Okay, just one more slightly generalization of this Gaussian form is something called a linear Gaussian. That means we have talked about two groups of variable and we have talked about how their variances changes. Now let us do it like this. It is as if you have two variables x and j, and the x is some constant a times z plus b, a linear function of z, x. Okay. So if I know the probability distribution of z, what is the probability distribution of x? And it turns out that we'll see next, but whatever be the probability distribution, if we do this kind of linear transformation, some properties like expectation, covariance, they are of a simple form. Okay, so if the covariance of z is mu, expectation or mean of z is mu and the covariance is sigma, then the expectation of x is a mu plus b, covariance of x is a sigma a transpose. Okay. This again, I mean, I have said before that marginal, so you can always get marginal distribution of x given z. So it's like one variable is known, what is the other variable? If we combine these two, this linear property and this previous thing, you get something called a linear Gaussian model, which says that you have one random variable z, which is Gaussian, and you have two constants a and b. And you have another epsilon, which is called a noise, which is also a Gaussian with zero mean and some L inverse sigma, rather precision. Okay, so now we are interested in this quantity. Suppose I have observed z. What is my probability? So I am interested in the conditional probability x given z. Okay, from the previous two discussions, you can derive easily that if z is Gaussian according to this and epsilon is Gaussian according to this, then x given z is also a Gaussian with the mean az plus b. Note that z is fixed, so the mean is az plus b, is a kind of closed mean, and the variance, very interestingly, is no longer dependent on the variance of z. It is dependent on the variance of this epsilon, as I have said, because z is already given, it is no longer stochastic, it is known. Okay, what is x? X is now the stochastic part of x is only coming due to epsilon. That's why only this epsilon is there. All right, so here again you can, this is also a very common model. You can also do a marginalization. You can also do the posterior. That means what is z given x. You can also do the marginalization, marginal likelihood x. Again, if you apply the definition and take this Gaussian function, you get all these expressions. All right, so this is the final discussion on this Bayesian, final probability distribution we will study here in this Bayesian thing. So what we have done is that next we have looked at gamma, we have looked at beta, we have looked at Gaussian. Now we'll take a general family of distribution or a class of distribution to which all these Gaussian and beta and gamma, they belong to. They have the same algebraic form. What is the algebra? This family is called the exponential family because of the exponent. This has a general form like this. So if theta is your distribution parameters, the likelihood function, which is x given theta, is 1 by some z theta, it is a normalizing term, times some function of x, hx. I'll explain what these individually are. Hx e to the power theta t. Theta t is a parameter of the function. Okay, so theta is a parameter of the function, theta t, into some function phi of x. I'll explain what these are. Some function phi of x. Sometimes it can also be expanded in terms of like this. Some hx, some function of x, into e to the power some function theta t into some function phi of x minus a of theta t. Note this, phi x minus a theta t into theta t. The whole thing e to the power something, and preceded by an hx. Okay. So this theta t is called the natural parameter or canonical parameter. this phi x is a sufficient statistics. It is another random variable. It is a sufficient statistics. Why it is called sufficient statistics? Because p x theta should be a function of theta as well as x. The way it is function of x is in terms of only this phi. Only this phi. So this phi is a general form of what is called a sufficient statistics. This constant z theta is a normalizing term, sometimes called a partition function. Log of z theta, moment we move it to the exponent, is called a log partition function or a cumulant function. This is also a normalization. Hx is kind of a marginal likelihood, which is a constant. It doesn't depend on theta. It depends on only x. Okay. So this is a very general form. You should read this maybe 3 or 4 times to understand what this form is. We'll see how many of the distributions we talked about are actually of this canonical form. Okay, so this is the canonical exponential form. Let us look at the binomial distribution. What is the binomial distribution? Is n choose x, mu to the power x, 1 minus mu to the power n minus x. Okay, this is the binomial distribution. All right. So if we, how do we express it in this exponential canonical form? You take e to the power log of binomial expression instead of just writing binomial expression, e to the power log of binomial expression. So because I need this e, so if I need this e to the power log of n by x mu x, this, just do the algebra, expand the log term, it becomes this, and this log of nx comes out, e to the power log of nx comes out, n choose x, e to the power x log mu by 1 minus mu minus n log 1 minus mu. Now compare it with this form, right? So what is hx? Hx is n choose x. What is theta tx? Theta tx is log of mu by 1 minus mu. Okay. What is phi x? Phi x is just x here. Okay. What is a theta? A theta is minus n log of 1 minus mu. This is a theta. Let us look at the Gaussian, which is more close to this. So this is the Gaussian distribution, 1 by 2 root over 2 pi sigma square e to the power x minus mu square by sigma square. And if you do it, hx will be 1 by 2 pi. What is theta? Theta is this natural form of mu by sigma square minus 1 by 2 sigma. Okay, this is theta. What is phi x? Phi x is x. If you look at here, it is x and x square. Note that this phi x I call sufficient statistics. You note that to estimate a Gaussian distribution, the sufficient statistics are the mu and sigma, which is the first moment and the second moment. What is a theta? A theta is this particular form. All right. So you can, there are many other distributions which belong to this family, Bernoulli, beta, everything, all of these are exponential. So all the distributions we have studied so far are actually exponential distributions. Okay. Uniform is not an exponential distribution. Okay, so if we do all this, you can easily show that if your prior is an exponential family and your likelihood is an exponential family, they are conjugate. The posterior is also an exponential family. Okay, so all members of the exponential family are conjugate to each other. They are a closure. There is a closure. They are conjugate to each other. And if you do the MLE and other thing, the maximum likelihood estimate, then you see that the MLE estimate is just dependent on the sufficient statistics, which is easily maintainable. Okay, so MLE on exponential families are computationally easier. Again, I am not going through the steps. You have to go to the slides yourself. And this is the so basically MLE just needs the moments. It's a function of only the moments, the sufficient statistics at the moments. You can do a full posterior estimation. So suppose this is your exponential form. Your posterior will also be exponential with additional parameters we call tau naught and nu naught, which are this nu naught is kind of pseudo observations coming from the prior, and T naught is a total sufficient statistics, sum of all the sufficient statistics. Okay, so this again you work out. So see, due to lack of time, I'm not doing it. These are not very difficult. You just have to work out the algebra. But you have to do it, otherwise you won't be able to solve the problems. So if I do the same Bayesian reasoning on this exponential family, you get the posteriors are also exponential, and they have a very nice form, which we have observed in all our previous examples. They have this new not-tau-not form, pseudo observation and sufficient statistics form. Okay, so I am again not going through this. You can go through this algebra. You can also compute the PPD. I'm not going through this. Okay, so now let us quickly summarize. So this is the last lecture on Bayesian estimation. All the methods I discussed so far are called as single node models. That means all the variables, say temperature, pressure, the vector variable, they are kind of treated as a single variable x. I call a node, a single node. I am, except for the last discussion on the block variables, I have not looked into the vector. How are the individual variables of the vector, how are related to each other? That's why everything blocked together I call as a single node model. In the next part, we'll see two node models where you have two blocks, XA, XB, and they interact among each other by some age or something, two node model. And then later we'll go to multi-node or graph models. So we did the following. We are interested in the likelihood probability, the prior probability, the posterior probability, the predictive probability, and model comparison or model averaging. The prior is the knowledge, likelihood is the data, posterior is combination of both. And then usually the prior will have some hyperparameter. So what you have done so far, you might be wondering, what I all did was assume some distribution, multiply and do something. The thing is, this is how Bayesian statistics is done. You have knowledge. This is a drawback also Bayesian statistics. You have to assume some distribution form. You have to assume Gaussian or beta or something. The assumptions are true or not, correct or not, nobody knows. But if they give you good estimates, you are okay with them as long as they give you good estimates. So I have, what the Bayesian statistics, this is a limitation. It's parametric. You have to assume some parametric form. You have to assume this form, beta or Gaussian. But what Bayesian statistics does is that once you have assumed this form, what is the correct parameter value? What is the correct hyperparameter value? Given this parametric form, that you can find out using the Bayes rule by this posterior into prior, that you can find out. You can find out either as a point estimate, or you can find out as an full estimate, full Bayesian estimate as a distribution, which captures all the uncertainties. Okay. Point estimates are often derived from these distribution estimates by some maximization or some aggregation procedure. If we take the full estimate, it's called a generative model, in the sense that you give the full distribution. That means you can as if generate a new data. It's called a generative model. We have looked at some particular cases, a Bernoulli, which is a simple coin toss, then a dice, which is a multinomial, then continuous variable Gaussians, and finally generalization of all these three into the exponential family. And we find that if we stick to this exponential family, then you usually have conjugate priors. And if we have conjugate priors, the posteriors have nice closed form expressions in the form of pseudo observations, the priors, and the sufficient statistics, which comes from the data. It's a combination of you. Actual algebraic form are there in the slides. I don't have time to do them. You have to do it. Thank you. I'll just stop the recording. If you have any questions, you can quickly ask.